the dark side of the universe. On the hunt for the ultimate cosmic monsters. While scientists scan the heavens, advanced computer simulations reveal the strange power of the black hole. Venture beyond the point of no return. To nature's ultimate no man's land. Welcome to our neighborhood. The Milky Way is just one of over 100 billion galaxies in the universe. And our sun, it's just one of over 100 billion stars in the Milky Way. We used to think of each star like our sun, as a friendly beacon amid the long night of space. Now, we know better. The universe wields violence beyond comprehension. Forces capable of tearing space and time to shreds. Join us now on a journey to the dark side, straight inside a black hole. Cape Canaveral, Florida. Our quest to understand black holes is about to enter a whole new dimension. Tucked into the nose of a rocket is a telescope called SWIFT. Its mission? To hunt for perhaps the most elusive objects in the cosmos. Black holes are so dense, not even light can escape their gravity. They defy detection. But today, hopes are riding high.
7, 6, 5, 4, 3, 2, 1. We have ignition, and we have
Scientists are counting on SWIFT to transport them to the frontiers of human knowledge and beyond. How do you find something that hides in the dark? You have to look for its telltale signs. SWIFT's instruments are designed to record bursts of high-energy radiation. Gamma rays don't penetrate Earth's atmosphere, but out here in space, SWIFT's view of them is front row center. They erupt when a black hole is born. That happens when a large star dies in a blaze of glory called a supernova. It's an explosion so powerful, it's as bright as a billion suns. What triggers that chain of events is the force that rules the cosmos: gravity. Scientists used to think of gravity as some kind of mysterious power that objects like the sun project across space. But what if it's space itself that gives gravity its pull? That's the way one man saw it. To Albert Einstein, space is a bendable four-dimensional fabric he called space-time. And gravity? That's the warping of the fabric by massive bodies. They literally put a dent in space-time. Objects get caught in their groove and simply drop into orbit. Einstein's theory was a radical notion, all the more when taken to its extreme. Just how warped could space get? Scientists found the answer in a singular class of star, more than 25 times the mass of our Sun. It's earned its name, a red supergiant. This star will live only a few million years, a fraction of our own Sun's lifetime. Deep inside, the crush of gravity sends temperatures soaring above 1 billion degrees. Lighter elements fuse into heavier ones. Hydrogen becomes helium, becomes carbon, on up to iron. The core grows so heavy, it buckles in on itself. Then, the collapse sends a shock wave roaring out. The star digs itself deeper into space-time as a black hole forms at its center, and the giant goes supernova. When the dust settles, what's left is a black hole, an object 1 million times the mass of Earth, but 1 million times smaller. A black hole is literally a puncture in the fabric of space-time. Venture closer, and gravity becomes a riptide. It's like riding a raging river that's pulling you faster and faster toward a waterfall. The closer you get, the stronger the current. You're headed for a point of no return. In cosmic terms, it's called the event horizon. Over this edge, there's no escape, not even for a beam of light. Black holes are gravity to the max, and yet they are altogether commonplace. Astronomers have actually detected dozens of black holes in our galaxy. They estimate there are tens of millions more. But then gravity doesn't stop there. It turns out there's a whole other breed of black hole out there. Peering into galaxies beyond our Milky Way, astronomers have found that nearly every one harbors an immense black hole at its center. One galaxy steals the show. It's called M87, and it's got a black hole 4 billion times the mass of our Sun. It has left its signature, a powerful jet erupting out at nearly the speed of light. Where does a hole this ferocious come from? To find out, turn back the cosmic clock 14 billion years to the beginning of the universe. The Big Bang. Matter and energy rush outward as the universe expands. To learn where supermassive black holes came from, scientists have recreated these early times with supercomputer simulations. They can trace the long, steady process that formed galaxies. From the start, gravity reigns in the cosmos. It draws together the primordial gases. These aren't gentle clouds. As they grow more and more dense, they heat up. Over millions of years, they become hot enough to ignite. The first stars are born. They end their lives in powerful supernovas, while their cores collapse into black holes. Billions of years later, and across billions of light years, Swift is today scanning the heavens for these same early supernovas. It's helping us learn what became of those black holes that formed in their wake. Astronomers believe some grew huge by plowing their way to the centers of their host galaxies, where they gorged on a rich supply of gas and stars. Some black holes grew larger still when they crossed paths with others. This scientific simulation traces the collision of galaxies, a drama that plays out over 2 billion years' time. The two galaxies become one. The black holes in their centers merge into a single powerhouse of staggering size. The gas hurtling into it gets jammed, heats up, and erupts in ferocious waves. Blast waves from supermassive black holes can stretch for thousands of light years into space. They may lay the framework of the new galaxy, sculpting its size and shape and stocking it with something unexpected. Black holes may be one of the chief ways galaxies get seeded with elements generated by stars, with carbon, oxygen, and iron, the stuff of solar systems, and us. So, how did our galaxy make out in all this? Astronomer Andrea Ghez wants to know, have we got a supermassive black hole of our own? For more than a decade, she and her team have been coming to the heights of Hawaii's Mauna Kea volcano to find out. Working at the giant Keck telescope, Andrea is tracking a strange presence in the center of our galaxy. A group of stars is swirling around it, and she's clocking their speeds, projecting their orbits. Her telescope is so powerful it can peer through the thick of the Milky Way, through 26,000 light years of cosmic dust, all the way to the stars at the galactic center. Whatever's got them in its grip, it's accelerating the ones closest to speeds of up to 3 million miles per hour. Given that, Andrea and her team calculate that the culprit weighs in at almost 4 million times the mass of our Sun. Solid evidence that at the exact center of our galaxy lurks a supermassive black hole. Andrea has confirmed the black hole is there without actually seeing it. So we're left to wonder, what's it like up close and personal? We can stop wondering and pay the monster of the Milky Way a visit. There's no spacecraft heading there anytime soon, but that's not stopping us. We'll get there courtesy of the latest telescope observations and computer models. We're just leaving the suburb where we live, about halfway out from the center of the galaxy. The Milky Way stretches before us. It's so large that it takes a beam of light 100,000 years to cross from one end to the other. Next stop, our galaxy's central hub, brimming with stars, known simply as the bulge. The farther we travel from our quiet cul-de-sac, the more crowded it gets. Up ahead, it's one big traffic jam of dust, stars, and hot gas. And it's always rush hour. Approaching dead center, the way is already strewn with signs of havoc, supernova remnants, and swirling clouds. Our course so far has been charted by astronomers like Andrea. They've plotted the landmarks by how they register across the light spectrum, from radio waves to X-rays. But here, their observations reveal a no man's land, an inner zone cleared by the voracious appetite looming ahead. A cloud of super-hot gas is swirling round it. The black hole pulls the gas in, then spews much of it back out. Now things get really strange. What you are seeing is not the stuff of Hollywood special effects. It represents the first time scientists have visualized the journey into a black hole. Their guide is Einstein, and what his equations tell them. Space here is so warped, the black hole acts like a giant lens, twisting the light that scatters across it. At last, we cross the event horizon, the point of no return. But don't expect the inside of the black hole to be dark. Swirling within is a maelstrom of energy and matter. Hidden in the chaos is a single point where the black hole's mass is packed, known as the singularity. Now, imagine there's an eye to this storm, magically made calm so all the strange predictions of Einstein's equations can play out. We'd be greeted by a passageway, an escape hatch in space and time known as a wormhole. Through it, we enter a white hole. Here, the same twisted logic holds in reverse. Instead of being drawn in, all light and matter are flung out. But to where? A wormhole is just the thing for a science fiction character in need of a quick getaway to another universe. Unless the truth be told, the inside of a black hole is too violent a place for a wormhole to actually form, let alone for the likes of us to venture. This is nature's ultimate fury, destruction on a scale beyond comprehension. Or is it? In fact, it's simply the workings of a restless universe. A long time ago, when this black hole was young, powerful winds roaring from it seeded our galaxy with elements. They may have helped form a sun and planets, and some beings who could look into the sky and ask, what is a black hole? Our search for the answer is turning up dark mysteries and radiant revelations, secrets stolen from the other side of infinity. Welcome to Planet Earth. Journey into the workings of Earth's great life support system, the global climate. Learn what makes our world so conducive to life, and what ruined our sister planet, Venus. Explore the winds, the oceans, and the forces of nature that shape this dynamic Earth. Imagine the Earth is a machine, a system of cogs and motors, powered by the sun, batteries included. But our world didn't come with an owner's manual. How does it operate? What are the inner workings of this grand and elaborate system known as Planet Earth? And why is it so conducive to life? Scientists have launched an armada of satellites to help us understand what makes our world tick. They're discovering the answers strewn across its atmosphere, on every ocean and continent, in the far reaches of the solar system and beyond. the Earth is the sum of its parts. They were forged in distant furnaces of our galaxy. Supernova explosions. When ancient stars erupted, they showered the Milky Way with heavy elements: iron, calcium, potassium, the very stuff our bodies are made of. But supernovas are also thought to bombard the galaxy with lethal high-energy particles. What safeguards our solar system is our star. The Sun provides a shield stretching beyond the last planet in its orbit, a force field that deflects these cosmic rays. But these solar winds can be dangerous too, especially during outbursts called coronal mass ejections. Want a vision of Earth gone wrong? Just look at what solar storms do to our sister planet, Venus. They strip away lighter elements in its upper atmosphere: hydrogen, oxygen, and the molecule they form, water. What's left is a witch's brew of noxious chemicals, including thick sulfurous clouds. Down at the surface, Venus's atmosphere is choked with high concentrations of carbon dioxide. CO2 is a potent greenhouse gas that traps the sun's heat. It has turned Venus into a cauldron. With surface temperatures of almost 500 degrees Celsius, this is the hottest planet in the solar system. How has Earth avoided the grim fate of Venus? We can see the answer as the solar storm approaches Earth. Our planet has a protective shield all its own, a powerful magnetic field generated deep within its core. In fact, that's just our first line of defense. Much of the solar energy that gets through is reflected back to space by clouds, ice, and snow. The energy that Earth absorbs is just enough to power a remarkable planetary engine, the climate. It's set in motion by the unevenness of solar heating, due in part to the cycles of day and night and the seasons. That causes warm tropical winds to blow toward the poles and cold polar air toward the equator. Wind currents drive surface ocean currents. This computer simulation shows the Gulf Stream winding its way along the coast of North America. This great ocean river carries enough heat energy to power the industrial world 100 times over. It breaks down in massive whirlpools that spread warm tropical waters over northern seas. Below the surface, they mix with cold, deep currents that swirl around the undersea ledges and mountains. Earth's climate engine has countless moving parts, tides and terrain, crosswinds and currents, all working to equalize temperatures around the globe. But when tropical heat builds to extremes, it can be released in a fury. In August 2005, within a huge looping section of the Gulf Stream, Hurricane Katrina. This is a supercomputer model of Katrina, a tool for scientists to better understand the dynamics of the hurricane system. To visualize the flow of air into the storm, they release a series of virtual streamers. Those with lighter colors are warmer winds. As they rise, they collide with cooler air above and produce clouds. The winds increase the evaporation of warm seawater, which draws more and more heat from the ocean and causes the winds to accelerate. Moving around the eye of the storm, winds can reach speeds of up to 250 kilometers per hour. A powerful hurricane like Katrina can release as much heat energy every 20 minutes as a 10-megaton nuclear bomb. While storms release heat stored in the ocean, the moisture they stir into the atmosphere helps keep the rest of the planet warm. Water vapor traps solar energy, along with carbon dioxide, the same greenhouse gas that ruined Venus. The difference is that Earth has found a way to keep CO2 in check. We can see it for ourselves by flying down to the ocean. The special ingredient that sets Earth apart is called life. The oceans are chock full of it. Too small for our eyes to see, phytoplankton may be the most important living things on the planet. They take in CO2, driven into the oceans by waves or drawn up from the deep by currents. They release the oxygen, while absorbing carbon. The carbon then begins a journey up the food chain. Phytoplankton get eaten by zooplankton. To name a few, radiolarians date back to a time over 500 million years ago, when life exploded across Earth's oceans. Copepods are tiny bug-like crustaceans. With over 20,000 species, they are the single largest source of protein in the sea. Moving up in scale is a host of creatures smaller than the tip of your finger, including these octopus larvae. They get eaten by small fish. And they in turn by larger ones, like jacks. They are consumed by the largest predators in the sea: orcas, tuna, sharks. At each step in the food chain, the carbon that began as part of a diffuse gas in the air is passed on to larger and larger animals. The larger the body, the greater the mass of carbon. One creature goes all out. A humpback whale eats up to 1.5 tons of food per day. That's a lot of carbon. From whales down to tiny phytoplankton, marine life is part of a global system of removing CO2 from the atmosphere, then gradually releasing it back. The key to this carbon cycle is Earth's ability to store it long-term. A NASA satellite tuned to read chlorophyll, a chemical tracer for plant growth, shows the global biosphere in action. In sync with the seasons, plants take in vast amounts of carbon dioxide and release the oxygen we breathe. On land, the carbon can then find its way into the ground when plants and animals die and decay. The Earth, too, gets into the act. Exposed rocks take in CO2 when it rains. Erosion sends it into the oceans. If it becomes part of the marine food chain, carbon-rich matter can sink all the way to the sea bottom in the form of waste. Countless organisms like the salp, a jellyfish-like creature the size of your thumb, live and die each year. All the waste, all those bodies with their stores of carbon rain down onto the ocean floor. They pile up, layer upon layer. In time, these carbon-rich sediments can turn to oil or to rock like limestone. The carbon can return to the environment as CO2 if the rocks become exposed, or if they get pushed deep underground by the movement of Earth's crust in a process known as plate tectonics. The pressure and heat gradually build until the Earth begins to erupt. Every year, over 100 million tons of carbon dioxide is spewed into the oceans and atmosphere by volcanoes. Acting on timescales of a day to millions of years, the carbon cycle has helped make our planet habitable. But its success depends on life itself. We are how Earth works. If somehow the carbon cycle went wrong, what would Earth be like? The answer is a world away, on Venus. Here, the CO2 belching from volcanoes isn't going anywhere. Venus is like a house on fire, with the windows forever closed. The cause can be traced in part to those incinerating solar winds. Sheltered from those winds, Earth has kept CO2 levels in balance by absorbing and releasing it in roughly equal amounts. Lately, that balance has been shifting. The amount of carbon dioxide from human activities, including cars, power plants, and factories, now exceeds volcanoes by over 200 times. Much of that is from the burning of oil and coal stored in the earth for millions of years. Since the Industrial Revolution, the amount of CO2 in the atmosphere has increased nearly 40%, with most of that in the last 50 years. The result? Global temperatures have risen by almost 1 degree Celsius. That's enough to accelerate the melting of vast stores of ice on high mountains and in the polar regions. Since the 1980s, NASA scientists have methodically tracked the Arctic's seasonal changes. They've found it's lost a quarter of the area covered by ice in summer. What's left has also thinned dramatically. That's just the beginning of changes that could transform our world, with some regions getting more rainfall, others drought. Deserts expanding, natural fires becoming more prevalent, wildlife habitat shrinking, polar regions becoming forested. And as the ice melts, it drains into the oceans. By the end of the century, sea levels are now expected to rise as much as 1 meter, inundating coastlines around the world. As our impact on the climate has grown, we've also gained a new perspective on Earth. From space. Technology is allowing us to take stock of the elaborate, interconnected climate systems that protect our world and sustain it. Within the fold of wind and water, of time and tectonics, our planet has nurtured another extraordinary participant, life. Today, we are masters of a world revealing itself as more and more wondrous than we ever imagined. Even as we continue to explore its workings, we ask, is our goal to spend Earth or save it? They are eruptions so vast, so earth-shattering. They have changed the history of our planet. Mass extinctions, climate collapse, toxic mayhem. Experience Earth and the solar system at their most extreme in supervolcanoes. The Earth we see around us is a thin disguise. It masks a monster. Beneath the calm, beneath the surface, a fury is building. It's 74,000 years ago on the island of Sumatra, along the eastern rim of the Indian Ocean. All around are signs of the tension rising deep below us. Seismic tremors rattle the landscape. Vents of sulfurous gases have begun to open up across the mountainsides. The clock is ticking down the final moments of a giant's fitful slumber. An immense mass of molten rock is rising to the surface. Cracks in the earth form. Escape routes open. Lava and hot gas begin to pour out. This volcano, known as Toba, has exploded 3 times before in the last 1,000,000 years. This time, it will earn a rare distinction, a supervolcano. Seething from a crater nearly 100 kilometers long, giant columns of smoke and debris fill the skies. Over 14 terrible days, Toba blasts out nearly 3,000 cubic kilometers of ash and rock. 1,000 times more than the Mount St. Helens volcano in the year 1980. It is the largest volcanic eruption the world has known in at least 25 million years. The eruption spreads a thick blanket of ash over an area half the size of Europe. Hanging in the upper atmosphere is a dense layer of soot and smoke, blocking the sun for years to come. Toba's grim aftermath is a global cataclysm. The planet plunges into a volcanic winter. Average temperatures fall by up to 10 degrees Celsius. All that rains is falling ash as drought sets in across the tropics. It does not let up for perhaps 1,000 years. Scientists believe that Toba's wrath was felt as far away as Africa by our own ancestors. In the dark years immediately following the eruption, their food supplies dwindle. It's an age defined by a dramatic crash in their population. The Toba eruption may have brought the human species perilously close to extinction. What causes a supervolcano? The answer begins with the birth of our planet some 4.5 billion years ago. It happened in a swirl of debris left over from the formation of the sun. Amid the chaos of the early solar system, gravity drew together clumps of rocks and dust. Countless objects collided and fused. Each collision generated heat. Under the barrage of impacts, a fiery young planet formed, molten at first. In time, the impacts decreased. Earth's surface gradually cooled, but its interior stayed hot. To this day, heat energy rises from deep inside the planet, a vivid reminder of the fires that burn within. The heat escapes in part through volcanoes, especially along the outer rim of the Pacific Ocean. Here is the notorious Ring of Fire. To see the furnace that powers its volcanoes, peer inside the planet. The heat moves up through a vast middle region called the mantle. It punches through where Earth's crust is thinnest in the middle of oceans. That causes massive plates that line the surface to push apart. Along the Ring of Fire, these oceanic plates collide with thicker continental plates. They thrust down into the Earth, carrying with them volcanism's secret ingredient, water. Some rocks, when mixed with water, melt more readily. They form a reservoir of magma that can fuel a volcano. It's an elaborate chain of events that Toba took to an extreme. As the molten rock and debris is blasted into the air, the entire volcanic mountain range collapses down, creating an immense cauldron-shaped basin. Water and heat are the agents of change for a world that's still a work in progress. Earth is not the only one. Welcome to Triton, Neptune's otherworldly moon. With surface temperatures at minus 235 degrees Celsius, this is no place for lava to flow. Instead, volcanoes of water ice shower the landscape. On Triton, it's the geysers that qualify as super. They can blast liquid nitrogen at almost 700 kilometers per hour to a height of 8 kilometers above the surface. Some volcanoes on Jupiter's moon Io have plumes of escaping gas that reach 500 kilometers above the surface. If on Earth, they would rise above the International Space Station. What powers Io's eruptions looms on the horizon. Jupiter exerts a massive tug on Io's core, generating heat. Much of it escapes in the largest volcano in the solar system, known as Loki. It may have formed when an impact blew a hole in Io's thin outer crust. There are traces of volcanic activity on Mars, Venus, several moons of Saturn, and Jupiter, and in the past, even our own moon. But it's Earth that may bear the deepest scars. The most destructive volcano known in our planet's history took place in what's now Siberian Russia. Wind back the clock to the time of the eruption, 250 million years ago. All of Earth's land masses were joined together in a supercontinent known as Pangaea. It was the end of a spectacular period known as the Permian. That was a time when life on Earth ran riot. Amphibians and early reptiles flourished, including the ancestors of dinosaurs and mammals. Forests and swamps saw an explosion of insect species. Fern plants, dominant for eons, were beginning to give way to conifers and palms. The oceans brimmed with life's bounty as well. Amid vibrant coral reefs, a wide variety of invertebrates and fish inhabited the open water. Here was Earth in all its glory. Then, in the geological blink of an eye, it was over. Up to 70% of all species on land and 90% of marine species disappeared. Ecosystems around the planet collapsed in a mysterious blight called the Great Dying. What happened? Scientists believe that a broad plume of rising magma pushed toward the surface. When volcanic formations like this spread out, their energy dissipates. But imagine if instead that their tentacles rose and exploded as one in a sprawling supervolcano. Here was hell on Earth. A series of small eruptions generated 1,000 times more lava than the Toba volcano. They choked the atmosphere with carbon dioxide and methane gas. Global temperatures soared. The oceans turned acidic, their waters depleted of oxygen. The Earth belched deadly toxins, including high levels of mercury. Through the history of our planet, eruptions on this scale are thankfully rare. Could one happen now? The answer is a secret in plain sight. Visitors to Yellowstone National Park in Wyoming may never suspect they are atop one of the world's largest active volcanoes. Its legacy is written across scenes like this, the fabled Yellowstone River. The heat below softened layers of volcanic rock. catastrophic flood at the end of the last ice age then gouged out this spectacular canyon. All around, thermal energy is underfoot, like a pressure cooker gathering steam. It escapes in smoldering cauldrons, in spectacular geysers that can blast hundreds of feet into the air. In primeval hot springs laden with sulfur that simmer near the boiling point. We venture to Yellowstone to admire this thermal spectacle. Imagine if we could follow it down to its source. Surface water seeps into the ground, moving through cracks in the underlying rock. A kilometer below, the water enters layers of heated rocks, then shoots back to the surface. Deeper still, 10 kilometers down, are the upper reaches of an immense plume of magma. It's over 100 kilometers wide and 400 kilometers deep. Yellowstone has erupted time and again over the last 18 million years. Several have followed the same tripwire events that triggered Toba, the sudden release of large amounts of magma, the collapse of the land, and the rise of a supervolcano. Yellowstone is overdue. It may not erupt again for hundreds, even thousands of years. Still, scientists are watching for early signs. Earthquakes, rising heat, the restless stirrings of a planet under pressure. Yellowstone's geysers, like Old Faithful, remind us that someday, once again, the planet will vent its rage. Supervolcanoes may be rare, but the fury that fuels them is ever present. If science tells us anything about them, it's that when the next one does erupt, life on this planet will be forever changed. It was the Soviet Union versus the United States. The technological advances of the space race rippled through society. Computers, satellites, materials, missiles. But its greatest legacy may not be something we made. Rather, it's a collection of rocks that astronauts picked up off the surface of the moon. They have led to a whole new understanding of Earth's early years and of our moon's mysterious beginnings. It's the brightest object in the night sky. For millennia, the moon has defined the rhythms of life and animated our myths. It has played a central role in our planet's history by stabilizing Earth's rotation about its axis, and with its tides promoting the formation of ocean currents that shape our climate. And yet, within its brilliant light is one of the most vexing questions in all of science. Where did the moon come from? At the dawn of the space age, in the 1950s, there were three competing theories about the moon's origins. One held that it was part of the Earth, cast off by the rapid spin of our planet in its early days. Another saw the moon as a wayward object that floated through our solar system and was captured by Earth's gravity. A third idea held that the moon formed right alongside the Earth. Scientists from the Soviet Union and the United States sought to test these theories with a fleet of unmanned lunar probes, shooting pictures, taking readings, and crashing onto its surface. To settle the question, we needed to go down onto the surface of the moon, to see it with our own eyes, and bring a piece of it back to our labs on Earth. But the quest to obtain samples from the moon was fueled as much by science as by competition between the two nations. The race to space began on October 4th, 1957, when the Soviet Union launched a satellite called Sputnik, higher and faster than anything before it. Sputnik's beep was a wake-up call for the United States. It led to the creation of NASA and a mission to get an American into space. The Soviets then launched Sputnik 2. It was 6 times heavier and had a passenger, a dog named Laika. Surprising the world again, the Soviets launched a spacecraft on April 12, 1961, that carried a man into space, cosmonaut Yuri Gagarin. From 1957 till 1965, the Soviets routinely bested their American counterparts. To overtake the Russians, President John F. Kennedy had to aim high. He committed the United States to the goal of landing a man on the moon before the end of the decade. Nothing so grand is ever so easy. The Gemini program was set up to build the skills and technologies needed for a successful lunar mission. It had its share of mishaps and failures. The Soviets were working on their own moonshot with the giant N-1 launcher. It had a complex design that included 30 engines on its first stage, all of which had to work flawlessly and in sync. Testing on the different stages of the N1 started in 1968, followed by 4 full-scale unmanned launches. Meanwhile, the American lunar program pinned its hopes on the mighty Saturn V rocket. The first manned launch of the Saturn V would carry the Apollo 8 capsule to the moon and into lunar orbit. Apollo 8 coasted to the moon and successfully returned. Both nations now had a lunar landing in sight. On July 13, 1969, the Soviets launched Luna 15, the third in a series of robotic craft designed to land on the moon, analyze lunar dirt, and fly samples back to Earth. Apollo 11 blasted off 3 days later. Luna 15 arrived on schedule, but Soviet controllers kept it in orbit to check its onboard systems. On July 20th, 1969, Neil Armstrong and Buzz Aldrin began their descent to the lunar surface. Computer overload alarms caused the Eagle lander to overshoot its designated landing site. Flying above boulders as big as houses and running low on fuel, Armstrong took manual control and searched for a spot to touch down.
Four forward, drift into the right a little. Count a half. 30 seconds. Contact light. Okay, engine stop. We copy you down, Eagle. Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again.
The 2 astronauts were out on the surface about 20 minutes later. Just as the American astronauts completed their first walk, Luna 15 finally began its descent. But within minutes, communications ceased. The thinking is that it crashed into the side of a mountain. Neil Armstrong called stepping onto the moon a giant leap for mankind. But it's what he and other astronauts picked up that may turn out to be Apollo's greatest legacy. On this and 5 subsequent missions, the astronauts entered a world that's frozen in time. In the absence of an atmosphere, the rocks, dirt, and craters held evidence of events dating back nearly to the moon's birth. Meanwhile, as they walked and rambled about, scientists on Earth were taking a fresh look at the lunar surface. They noticed, for example, that some large old craters are surrounded by concentric rings. You can see them in this image of a feature called the Mare Orientale, captured recently by NASA's Lunar Reconnaissance Orbiter. The colors showed differences in elevation. Scientists began to suspect that the rings were created when an impactor splashed down on a molten surface. That gave rise to the notion that early in its history, the Moon's surface was a vast ocean of magma. When the astronauts arrived, they found relatively light rocks strewn about the surface. They could have been forced to the surface by heavier material that had sunk toward the Moon's interior. The rocks contained another important clue to the Moon's origins. They were found to be strikingly similar to those on Earth, in part because they share forms of oxygen that scientists regard as blood types for solar system bodies. A striking new theory emerged to explain the evidence. Early in the history of the solar system, the theory holds, Earth shared an orbit with a Mars-sized body called Theia, named for a titan in Greek myth who gave birth to the moon goddess Selene. When its orbit became unstable, it headed in Earth's direction. Theia hit at an oblique angle, causing the Earth to spin faster and debris from both Theia and the Earth to fly into orbit. When the dust settled, the debris began to coalesce in Earth orbit, forming the Moon. By then, volatile compounds like water had evaporated. The Moon then comes primarily from the mantles of the Earth and Theia. That's why, on the whole, it's lighter or less dense than Earth. From this violent beginning, the Moon gradually cooled and the magma that lined its surface hardened into a crust. Yet it was still subject to intense bombardment in the chaotic environment of the early solar system. The Apollo astronauts encountered a secondary effect of all the impacts. Rocks that were formed in the crucible of widespread volcanism. On Earth, volcanic eruptions are often powered by water, heated and pressurized during the movement of immense tectonic plates. Volcanism on the Moon is tied to impacts forceful enough to melt the surface and release material from the hot interior. When this happened, molten rock flowed out in thin, smooth layers that reached far from its source. That's how the Mare regions that cover about 1/6 of the entire lunar surface are thought to have formed. These immense volcanic basins date back to a period of large and violent impacts from 3 to 4 billion years ago. It now appears that impacts had made an even deeper impression. One new study seeks to explain the Moon's lopsided topography. The dark lava basins on the near side and the highlands on the far side. It holds that another much smaller body formed alongside the Moon at the time of its birth, and eventually merged with it. The violence of the merger literally rearranged the Moon's interior, pushing molten magma onto the near side, while adding an extra layer of crust to the far side. Apollo astronauts took the first step in studying the interior of the Moon by installing a network of seismographs. Scientists recently followed up by performing a kind of CAT scan of the Moon. They sent out a pair of spacecraft called Grail to orbit the Moon in unison. By measuring subtle changes in the distance between the craft, scientists can discern variations in the Moon's gravity. What they found was that the Moon's gravity is not smooth. Rather, it's pocked with regions that exert an especially strong pull. Grail scientists have now linked these regions to dense concentrations of mass deep inside the Moon, and these to large impact sites such as the Mare Orientale. Lunar impacts appear to have left an even more remarkable legacy. In the year 2009, the L-Cross probe arrived at the Moon aboard the Lunar Reconnaissance Orbiter on a collision course with the South Pole. It slammed into a crater. Seconds later, a trailing probe detected a tenuous cloud rising up from the crash site. Readings of this cloud showed that 5.6% of the crater floor consists of water ice. Most likely, it was delivered by comets that crashed into the Moon. It had survived over the eons in craters with steep sides that shield it from the sun. It turns out that may be just the beginning of vast hidden stores of water. Circling the Moon repeatedly aboard the Lunar Reconnaissance Orbiter, a Russian-made instrument called LEND has found evidence that hydrogen and perhaps water ice is embedded in lunar soils beyond the polar craters. And now, rocks picked up by the astronauts are telling an even deeper story. Analyzing them with new techniques, several teams of scientists recently found a compound called hydroxyl. It's H2O, but with only one atom of hydrogen. Based on this evidence, scientists estimate there is enough water locked up inside the moon to cover its surface in a layer 1 meter deep. The intimate connection between the Earth and the Moon appears to trace back to their earliest times. So far, we've really only scratched the surface of their shared history. The quest to understand that relationship was once part of the feverish competition of the Cold War. A whole new race to the moon is now heating up. This time, fueled by the search for valuable minerals and metals, mining and money. Russia, the United States, China, India, and Japan all have missions in development, including an array of manned missions.
Discovery's engines are now throttling down as the orbiter passes through the area of maximum pressure, reducing distress.
A number of private missions are also on the drawing boards. What will these missions tell us about our celestial partner and how it formed? Inevitably, the more we learn about the mysterious birth of the moon, the more we'll learn about its mother planet, Earth. Earth is a water planet. Vast interconnected bodies of water, the oceans, cover 71% of its surface. They moderate the global climate. They fuel storms that drench the land and feed the lakes and rivers that sustain us. And now, scientists have detected whole oceans of water hidden in rocks deep inside the planet. How did our world come to be endowed with such a rich bounty? Is Earth the only oasis in space? For as long as we have gazed upon the stars, they have offered few signs that somewhere beyond our solar system are worlds as rich and diverse as our own. Recently, astronomers have been discovering planets at a rapid clip. Using orbiting observatories like NASA's Kepler Space Telescope and sophisticated ground-based telescopes. These alien worlds range from great gas giants many times the size of our Jupiter to rocky, charred remnants that burned when their parent star exploded. Some have wild elliptical orbits. They swing far out into space, then dive in close to the scorching atmospheres of their parent stars. Amid these hostile realms, a few bear hints of water or ice. Ingredients needed to nurture life as we know it. The race to find these Earth-like planets has raised anew the ancient question whether, out in the folds of our galaxy, planets like ours are abundant and life commonplace, or whether Earth is a rare Garden of Eden in a barren universe. We can begin to find out by reaching back into the history of our planet, to the particular circumstances that endowed it with its stores of water. Beyond our solar system, even in the cold blackness of space, our universe is awash in atoms and molecules. They are the raw material of the evolving cosmos. The basic building blocks of stars and planets. In some regions, a nebula may glow with an eerie light of stars. These are places where new stars and solar systems are being born. Thousands of these glowing gaseous clouds are scattered throughout the galaxy. Within their frozen interiors, atoms combine into more complex molecules. Ammonia, methane, carbon monoxide, and water. To astronomers, the presence of water, H2O, is no surprise. Oxygen, the fifth most abundant element in our universe, originates in stars that dominate many nebulae, known as red giants. Deep in their cores, high heat and pressure causes hydrogen and helium atoms to crash together to form heavier atoms like oxygen. When these stars die, they kick oxygen and other elements out into the surrounding region. About 5 billion years ago, within such a rich chemical soup, a medium-sized star, our Sun, was born. Within the swirl of gas and dust flowing into this newborn star, a solar system of planets, moons, asteroids, and comets gradually took shape. Today, you can find water in nearly every corner of our solar system. Pluto and its moon, Charon, are part of a class of small objects orbiting the outskirts of the solar system. They are leftovers from the creation of the planets. Their surfaces are lined with a thick layer of frozen methane and water ice. Further in, the blue planets, Neptune and Uranus, get their color not from water, but from methane clouds that lace their frigid atmospheres. Within them, charged particles circulate in a sea of liquid water, producing electrical currents and magnetic fields. These oceans probably resemble battery acid more than water. Within the folds of Saturn's rings are countless particles of ice. Hovering just above them is the moon Enceladus, with an icy surface that makes it one of the brightest objects in the entire solar system. The Cassini spacecraft detected a jet of water ice shooting out of its south pole. Scientists speculate that it's escaping from a liquid ocean beneath the surface. The largest planet, Jupiter, harbors its own storehouse of water. Though water exists in relatively small amounts in the giant planet's atmosphere, it helps fuel storms like the swirling Great Red Spot. Jupiter's storms are the result of water vapor rising and falling like thunderstorms on Earth. Beyond Jupiter's roiling atmosphere, beyond its volcanic first moon, Io, lies a water world, Jupiter's moon, Europa. Its bright, smooth surface is crisscrossed by channels and grooves that are thought to have been carved out by shifts in an ocean of liquid water or slushy ice that lies below. The moon likely has an inner heat source, friction from the tugging of Jupiter's gravity on its rocky core. If life forms inhabit this inner European sea, they are surely very primitive. in toward the sun, the asteroids are little more than jagged cinders of rock and iron, yet they are laced with very small amounts of frozen water. Even on the hot planet Mercury, you can find ice tucked into polar craters that shield it from the sun. Likewise, spacecraft have detected ice in abundance on the lunar poles. Rocks brought back by the Apollo astronauts contain evidence that the interior of the moon may well be laden with water. Then there's Mars, at the outer edge of what scientists call the life zone. Enough solar heat reaches Mars for liquid water to flow. And from networks of ancient dry riverbeds, scientists believe that water once flowed here. And yet, today, Mars is cold and dry. In summer, dust storms scour the surface with hurricane-force winds. In winter, frozen carbon dioxide frosts the landscape. If there's any water left on Mars, it's most likely been absorbed by rocks below the surface. Venus, on the inner edge of the life zone, is similar to the Earth in size, mass, and composition. Yet its thick clouds shroud an awful reality. Clouds rain drops of sulfuric acid, not water, onto the landscape. The clouds pass some sunlight, but the thick carbon dioxide atmosphere prevents most of the heat from escaping back into space. This greenhouse effect traps enough solar energy to turn Venus into the hottest planet in the solar system. What water there is can't last. The Venus Express spacecraft found that solar winds steadily strip off lighter molecules of hydrogen and oxygen. They escape the planet on the night side, then ride solar breezes on out into space. Mars may suffer a similar fate. What makes our planet so different? For one thing, Earth is enveloped in a magnetic field generated deep in its core. It deflects the solar wind like a protective shield. Unlike Venus, water, inherited from the ancient nebula, has been able to flow on this small, rocky world since its early days. Today, water in all its forms dominates the planet. It is tied up in ice caps at the poles where it grows and shrinks with the seasons. It ebbs and flows in the oceans and in lakes and rivers, covering 3/4 of Earth's surface area. And it floats in the atmosphere in clouds of water vapor. When sunlight hits the Earth, water vapor absorbs some of the energy, holding the heat in. Another crucial ingredient in our atmosphere acts as a thermostat, a control knob to keep the climate from overheating or freezing over. The trace gas carbon dioxide absorbs enough energy to prop up global temperatures and allow water to remain in the atmosphere. But the Earth did not come gift-wrapped with this balance of CO2. In its early days, the Earth was packed with volcanoes that released huge volumes of CO2 and other chemicals into the air. In time, some CO2 was removed by chemical reactions between rocks and water and washed into the sea. That allowed another crucial factor to come into play. Deep in the ocean, primitive life forms evolved, with the ability to take in carbon dioxide and emit oxygen in the process of photosynthesis. So it's not enough for a planet just to have water. The ability to cycle carbon in and out of the atmosphere and regulate a global climate is perhaps the highest bar that an alien planet must reach to be called Earth-like. Over the millennia, we have learned how to explore our water world. But the tools of exploration have changed, and today we are looking outward to space to search for planets like ours beyond our solar system. Are there other water worlds like our own? Do they support life, human or otherwise? A number of tantalizing hints have emerged. In studies of stars such as Kepler 6.2, 1,200 light-years from Earth. Using the Kepler Space Telescope, scientists recently detected 2 planets orbiting this star that are only slightly larger than Earth. They are both within the life zone. Do these worlds resemble Earth with its magnetic field, its climate, and its vast stores of water? Or have they gone the way of Venus, Earth's sister planet, with its dense hothouse atmosphere and barren landscapes? As we cast our gaze across the reaches of space and time, our search for life goes on. We watch for the unique signatures of a world like ours, as we scan the galaxy for another oasis in space. Since the dawn of the space age, we've imagined traveling to worlds beyond our solar system. Touching down on eerie landscapes, encountering alien life forms, what was once science fiction is now becoming science fact. Each year, we are finding more and more planets around other stars. Some strange and hostile. A few with the potential to harbor life. What can we learn about the universe and about ourselves? As we scan the galaxy for undiscovered worlds. In the last 2 decades, precision telescopes have allowed us to see into the bright light of distant stars and detect the presence of planets. This is 51 Pegasi, a sun-like star about 50 light-years from Earth. In 1995, from slight variations in its light, astronomers discovered a planet orbiting around it. For the first time in human history, we knew for sure that ours is not the only solar system. The planet they found is huge, more than 100 times the size of Earth. Yet it orbits astonishingly close to its parent star. Its atmosphere is a scorching 1,300 degrees Celsius. Whipping around its star every 4 Earth days, this exoplanet defied everything we thought we knew about solar systems. Our solar system began to take shape around 4.5 billion years ago. In a giant cloud of dust and gas. Over millions of years' time, this cloud collapsed, and the sun was born. The cloud flattened into a spinning disk. Inside it, dust and rock collided, forming the inner planets. Farther from the sun, hydrogen and helium gas collapsed into dense centers, forming the gas giants: Jupiter, Saturn, Uranus, and Neptune. The planet at 51 Pegasi, known as a hot Jupiter, is huddled too close to its parent star to fit this pattern. One theory suggests that it formed far out in the solar nebula, but gradually migrated inward. We have much yet to learn about worlds like this, but with each new one we discover, we move a step closer to understanding planetary systems. Astronomers found this planet by searching for clues hidden in the light of its parent star. The planet exerts a gravitational pull, causing the star to wobble slightly. At our telescopes, the star's light passes through a spectrograph, an instrument that breaks the light up into component colors like a prism. The result is a spectrum that shows patterns of lines characteristic to the star. As the star wobbles, these lines shift back and forth, toward blue as the star comes closer, and toward red as the star moves away. Today's instruments are so sensitive that they can measure differences in a star's speed as small as 1 meter per second, the speed of a person strolling down the street. Each wobble represents a complete orbit by the planet around the star. Based on what they know about gravity, astronomers can use this information to estimate the planet's mass and its distance from the star. That's not the only way to detect these far-off worlds. Take the star HD 209458. Astronomers had already found a hot Jupiter with the wobble method. In 1999, this exoplanet was observed passing in front of its parent star in an event called a transit. Astronomers noticed that the star's light dipped slightly, but regularly, every 3.5 days. This dip in its light was tiny, only 1%. But it meant that a planet was there, making one orbit every 3.5 Earth days. Since larger planets block more starlight, astronomers now had a direct way to measure the exoplanet's size. The planet HD 209458b turns out to be less massive than Jupiter, but it's about 30% larger. It is less dense, or puffier, than any planet in our solar system. That discovery led to new techniques for studying an exoplanet's atmosphere. When the light from the star passes through the atmosphere of the planet's atmosphere imprints upon that light a signature of whatever atoms and molecules are present. In this case, instruments aboard the Hubble and Spitzer space telescopes detected sodium, hydrogen, methane, water vapor, and possibly carbon dioxide, a collection of molecules that elsewhere might be associated with the presence of life. Using transits, we have tools that in theory could detect the signatures of life on a rocky Earth-like world. From what we know, it takes a particular set of chemical building blocks, including molecules containing carbon. Add in a source of energy like a star and liquid water. Around each star is a so-called habitable zone, in which planets are bathed in just the right amount of solar energy for liquid water to flow. Where can we look to find planets with solid surfaces and temperatures that allow liquid water to flow? With literally billions of stars in our Milky Way to choose from, the possibilities may seem endless. But they aren't. Supergiants are the hottest, most massive stars. They're far too unstable and short-lived, and life probably wouldn't have enough time to develop on a planet that orbits it. They are known to explode in supernovas that would obliterate a planet. We can also rule out most double or triple star systems, which make up more than half of the galaxy's stars. With two stars tugging on a single planet, its orbit would probably not be stable enough for life to develop. And the combined light from two or more stars makes these planets even harder to find. What about red dwarfs, the most plentiful stars in our galaxy? They are smaller and cooler than our sun, but don't emit very much light or heat. Still, they live far longer than the sun. A red dwarf solar system could survive and evolve over billions of years' time. In the year 2009, astronomers made their first discovery of a rocky exoplanet orbiting a red dwarf star. Called Corot 7. The world goes around its sun in just 20 Earth hours. With surface temperatures at around 2,000 degrees Celsius, this extreme world is probably lined with molten rock. Massive rocky exoplanets like Corot 7b, known as super-Earths, are some of the strangest, most exotic worlds yet detected. Calling it a super-Earth doesn't mean it bears much resemblance to our planet. Most detected so far are simply too close to their central star and too hot for life to survive. There is one newly discovered solar system that may come close. The red dwarf star Gliese 581 is relatively close to Earth, at 20 light-years away. A team of French and Swiss astronomers had been studying its light from a telescope in the mountains of Chile. They noticed a slight jitter, the gravitational tugging of planets. They first deduced the presence of Gliese 581b, a planet with 16 times the mass of Earth. At a distance from its central star of only 6 million kilometers, it's bound to be very hot. Then came Planet C, 1.5 times the size of Earth, with an orbit of 11 million kilometers. Its position just inside the life zone means it's probably too hot. Then there's Planet D, 7 times the mass of Earth at 33 million kilometers from its sun. At the outer edge of the star's habitable zone, it receives only 30% of the light that Earth gets from our sun. Imagine a much larger version of Mars. A planet with a thin atmosphere, no liquid water on the surface, and temperatures that average around -59 degrees Celsius. Some astronomers suspect that Planet D is an icy world that migrated in from the outer solar system. On the other hand, what if Planet D possessed some of the attributes of our planet? Geological activity that produced an atmosphere, a moon to stabilize its orbit, and a robust magnetic field to shelter it from solar winds. In the future, as our instruments become more and more sensitive, astronomers will look for signs that it has an atmosphere, and within it, chemical compounds that might be associated with life: methane, carbon dioxide, water vapor. It's not out of the question that we, or a robotic emissary, may one day be able to visit and get a closer look. It's possible that Earth-sized planets, maybe even habitable ones, are commonplace in our galaxy. Given the immense distances and the brightness of their parent stars, the trick is finding them. Until recently, our technology and methods were best suited to detecting massive planets. But that's changing. Launched in 2009, the Kepler Space Telescope was designed to look specifically for Earth-sized planets in the habitable zones of their parent stars. Kepler measures light from 100,000 stars like the Sun. Watching for minuscule dips in starlight, the telltale sign of an exoplanet transit. The mission has already discovered an array of giant planets with orbits lasting days or weeks. Astronomers will be combing their data in the years to come for signs of Earth-sized worlds with orbits of a year or more. As astronomers continue to comb their data, they are finding a remarkable diversity of solar systems. Kepler-11, at 2,000 light-years from Earth, has 6 planets, all larger than Earth, packed into orbits smaller than that of Venus. Kepler-20 has 5 planets, 2 about the size of Earth, but all within the orbit of our Mercury. Then there's Kepler-47, a double star system with 2 planets discovered so far. The innermost planet, the smallest detected by the transit method, is 3 times the size of Earth, but it's so close in that its year is 50 Earth days. Farther out, with an orbit of 303 days, planet C is in the life zone of its star. Unfortunately, it's a gas giant a little larger than Neptune. We continue to ask, are there worlds like ours somewhere out there? We now have the technological capability, the telescopes and the computers that will begin to help us answer that question. Whether we find that Earth-like planets are commonplace or rare, there is one thing we know with certainty. Our world is but one tiny grain on the beach of a cosmic sea. Looking in any direction, the universe goes on and on for incomprehensible distances. So far, billions of years have whispered by this small corner of the galaxy. billions of years will transpire after we all are gone. Our moment of life is like a breath of air. As we look up into the night sky, we wonder what new worlds await our discovery. And what light will they shed on the origin and evolution of our own Earth? Peering deep into the universe, astronomers probe the clash of cosmic forces. The obliteration of matter and energy. We glimpse the limits of time and space in the strange death of a star. There is no vision more reassuring. The endless cycles of the sun and the moon. The heavens ceaselessly turning. The night sky appears eternal and unchanging. Modern astronomy has given us a much different vision of a universe that roils and vents its rage. That vision comes together in the death throes of a giant star. Its surface is a stormy sea of fire. As superheated gas rises and sinks. Giant waves form. Solar tsunamis 1,000 kilometers high. Immense loops of hot, electrified gas, larger than the Earth, blast into its atmosphere. Deep within its core, the star has begun to collapse in on itself. That causes the star to erupt in a violent supernova. In its wake, the explosion leaves a trail of colorful filaments and luminous, billowing clouds. Remarkably, the death of one star gives rise to a whole new generation of others. This cycle of death and birth has defined the history of our Milky Way galaxy and that of billions of other galaxies in the universe beyond. Our own vision of space has been shaped by a handful of rare exploding stars bright enough to be seen by the naked eye. In the year 1054, stargazers in North America spotted a supernova near a crescent moon. The same event was recorded in China, Korea, and the Middle East. The astronomer Tycho Brahe saw one in 1572. He wrote, "I was led into such perplexity by the unbelievability of the thing that I began to doubt the faith of my own eyes." Johannes Kepler recorded the next one in 1604. Galileo used it to make his case for a whole new approach to astronomy, based on the idea that change is a fundamental part of the cosmos. To find out how stars shape our universe, astronomers are employing an arsenal of new technology. From giant telescopes perched on high mountains to a fleet of instruments in space. When we look through a telescope at the stars, we are seeing the visible light they emit. But this is just a small part of what is known as the electromagnetic spectrum. At one end of this spectrum are short, high-energy X-rays and gamma rays. At the other end, long, low-energy radio waves. Huge arrays of radio telescopes are now being used to collect low-energy radio signals emitted by stars far off in the universe. Scientists use them to look through nebulas and gas clouds, to see the objects inside. At the other end of the spectrum are ultraviolet, X-rays, and gamma rays. The short wavelength of X-rays allow doctors to send them through our bodies to look for bone fractures. Astronomers look for them in space as evidence of the most violent processes in our universe. What shapes the cosmos at large is visible close to home. Our Sun is a medium-sized star with a surface temperature of nearly 6,000 degrees Celsius. Deep within its core, the temperature rises to 15 million degrees Celsius. High heat and pressure initiate nuclear fusion reactions that convert hydrogen to helium, releasing energy. The sun, like all other stars, spends its life fighting gravity. Energy pushing out from its core keeps its outer layers from collapsing in. The sun produces enough energy to hold gravity in check for billions of years. Not so for a large star. It burns hot and fast, steadily packing its core with heavier and heavier elements. When its core reaches a critical threshold, it no longer produces enough energy to counter gravity. It collapses, then explodes. Destruction is by no means a supernova's only legacy. The explosion seeds its environment with carbon, oxygen, iron, and other elements necessary for life as we know it. Shock waves from the blast can trigger the birth of new stars. In fact, star hatcheries set in motion by supernovae percolate all around our galaxy. Among them is a great luminous cloud of gas and dust known as the Orion Nebula. Here, astronomers have pinpointed solar systems in the making. When clouds like these become dense enough, nuclear fusion begins. Stars and solar systems are born. Another fate altogether awaits the exploding star at the center of this cosmic drama. In the wake of the blast, its highly compressed core remains intact. Imagine planet Earth compressed down to a tennis ball. That's a neutron star. Some can spin at incredible speeds, hundreds of times per second. When a so-called pulsar was first detected by radio telescopes, its signal was thought to have come from a faraway alien civilization. The Crab Nebula is the shell of the same supernova that caught the attention of so many cultures in the year 1054. Scientists have zeroed in on a pulsar deep within. They documented waves of radiation that have etched circular patterns in the surrounding gas. Some dying stars meet a fate that is stranger still. Nature, it seems, has contrived a monster. The scientist Albert Einstein once speculated about a star with such intense gravity that nothing, not even light, could escape its grasp. He dismissed this prospect as impossible. What once seemed beyond reason now defines the frontiers of science. Astronomers believe that when a star explodes, enough matter can collapse into its core that it literally exits the known universe. Gravity wins the final battle. From our vantage on Earth, we define our universe by familiar criteria, including the forms of light we find along the electromagnetic spectrum. But black holes defy discovery. How can we detect an object that emits no light? Astronomers spotted the answer in a flash of gamma radiation in the direction of the center of our galaxy. Radio telescopes zeroed in on the source and found jets of matter racing out in two directions. This is what they saw. A black hole that is drawing a stream of gas from a star's outer layers. As it flows in, it forms a spinning disk. The disk generates magnetic fields that twist around and channel some of the inflowing matter out into a pair of high-energy beams, or jets. Astronomers now know that black holes can pack so much energy into these jets that they accelerate to within a tiny fraction of the speed of light. It turns out that this black hole, known to us as GRO J1655-40, is streaking across space at a speed of 400,000 kilometers per hour, 4 times faster than other stars around it. Most likely, it was blasted like a cannon by the supernova that produced it. Black holes, with their ability to marshal extreme energies, are more than just curiosities in our universe. There is a breed of large black holes that dates back to the earliest times, when the first generation of stars were being born at a rapid pace. When these primordial giants died, some gave birth to black holes. Gravity force-fed these black holes a diet of stars and gas as matter collapsed into the first galaxies, and as small galaxies merged into larger ones. A few of these primordial monsters grew to billions of times the mass of our Sun. By launching powerful jets, they heated up the regions surrounding their host galaxies. That put a stop to the flow of gas into the central galaxy, stunting its growth and allowing smaller galaxies on the periphery to form and grow. But the impact of these black holes did not stop there. This image from the Chandra X-ray Observatory shows a cluster of galaxies called Hydra A. It's enveloped in immense hot cavities glowing in X-ray light. There is a jet visible in radio waves blasting out of its central galaxy. Gas along the edge of the jet was found to contain high levels of iron and other metals, probably generated by supernova explosions. By pushing these metals into regions beyond, the black hole seeded more distant galaxies with the elements needed to form stars and solar systems like ours. Supermassive black holes can be seen in nearly every large galaxy in our universe. We've caught a growing number in the act of powering massive jets. We are beneficiaries of the violent life cycles of stars. And yet, we are separated from them by scales of distance and time beyond anything we experience on Earth. That separation is thrown into sharp relief by the flight of the twin Voyager spacecraft launched in 1977. After exploring the outer planets and their moons, these crafts are now plying the outer limits of the solar system. Tens of billions of miles from Earth. Traveling at 16 kilometers per second, Voyager 2 will pass within 4 light-years of the nearby star Sirius. 290,000 years from now. From our tiny corner of the galaxy, we've discovered that stars not only light up the universe, they also seed it with the stuff of life. By witnessing the explosive end of a star, we gain fleeting glimpses into the power that shapes the universe and transforms worlds like our own. Since ancient times, we have asked, what lies over the horizon and beyond the oceans? Where does the world end? As we've pushed farther and farther out, our journey has revealed a solar system, a galaxy, a universe on larger and larger scales. And now, a new set of theories is telling us that time and space are incomprehensibly large. What will we learn on our search for the edge of the universe? If you could step away from our world, what would you see? How do deserts fit in with oceans? Or mountains with floodplains? What structures connect Earth to the other planets? The stars, and beyond. The ancient Greek philosopher Aristotle believed Earth lay at the center of a series of 55 celestial spheres, with each moving in a way that predicted the positions of the planets or the stars within them. He saw these outer realms as home to the gods. They are made, he said, of a pure substance not found on Earth. The Greeks were also the first to see celestial events as natural phenomena, subject to human investigation. One skywatcher named Anaxagoras suggested that meteors are made of materials found on Earth and might have actually come from the Earth. He and other Greek astronomers helped build the foundations of science. But they would be shocked to see the discoveries being made by their counterparts today. The stars and planets that once harbored the gods are now seen as infinitesimal parts of a vast scaffolding of matter and energy that extends far out into space. Aristotle's model of a cosmos centered on the Earth lasted until the 16th century. Nicholas Copernicus proposed that Earth and the other planets instead revolve around the Sun. Based on his findings that planets have their own orbits, scientists constructed new models that describe their movements over time. Copernicus noted, too, that the firmament, the stars, lay far, far beyond the solar system. Our model of the universe began to get much larger in the year 1609. When the scientist Galileo Galilei used the first astronomical telescope, he observed that the Milky Way, a broad band of light that rises up in summer skies, is actually composed of stars. Centuries later, astronomers discovered that the Milky Way is actually a vast revolving disk. They characterized the universe as an island of stars and gas, immense, yet still limited in size. This model of an island universe would soon collapse under the weight of scientific evidence. Working with the huge new 100-inch telescope on California's Mount Wilson, astronomer Edwin Hubble and an assistant named Milt Humison analyzed the light of fuzzy patches of sky known then as nebulae. They found that these patches were actually galaxies unto themselves, but located far beyond our own. They also found that many of these galaxies are moving away from us. The farther away they are, the faster they are receding. This discovery sparked the rise of a whole new model of the universe, one filled with countless galaxies that's growing larger all the time. Because it takes the light of these distant galaxies millions, even billions of years to reach us. The deeper into space astronomers peered, the farther back in time they ventured. To study the history of the cosmos, scientists opened larger and larger telescopes to capture light from ever more distant reaches of the universe. They began to see that the stars and the universe at large are not as peaceful or static as we had once believed. In an age of atomic weapons and nuclear physics, a whole new model of the universe emerged. A dynamic realm shaped by giant exploding stars, shock waves, and black holes. In this view, the universe had its origins in a violent primordial event. A Big Bang. The Big Bang model rested on four main pillars. That the universe as a whole is expanding in all directions. If you turned the clock back, you'd see that all matter and energy had a common starting point in space and time. The existence of light elements like hydrogen, which would have formed in very early times and later converted to heavier elements. That there is light wafting through the universe that was emitted when the universe was young and has stretched out over time into microwaves. Finally, It established a time frame for the evolution of stars, galaxies, and the large-scale structures of the universe. But this new model of a Big Bang universe proved incomplete. Recent precision measurements gathered by the Hubble Space Telescope and other instruments have brought a consensus that the universe dates back 13.7 billion years. Taking cosmic expansion into account, galaxies at the edge of the visible universe are actually 46 billion light-years away from us in each direction. What's beyond those galaxies? They have their own horizons that extend that much farther out. What's beyond that? Where does it all end? And how did the universe grow to such an immense size? Another observation puzzled astronomers. No matter what part of the sky you examine, the spread of galaxies, the density of matter, and the temperature are the same on large scales. To achieve this degree of homogeneity over its entire breadth, the universe would have to have expanded far faster and to a greater extent than allowed by the standard Big Bang model. How did the universe get so big and so uniform? A new cosmic model with a fresh explanation was waiting in the wings. It sprung from one of the most important scientific observations of our time, linking the universe we see around us to its earliest moments. The Space Shuttle Discovery lifted the groundbreaking Hubble Space Telescope into orbit on April 24, 1990. Another, more modest launch took place 5 months earlier. The Cosmic Observation Background Explorer, COBE for short, was sent up to capture the microwave light that was emitted when the universe was in its infancy. This light, the mission found, contained a pattern of hot and cold spots. The WMAP and Planck satellites have updated this observation by recording greater detail. In these images, scientists found the seeds of all we see around us today. Smooth on a large scale, but with variations on smaller scales. Astronomers set out to discover how the universe would have evolved from this cosmic template. In an age of computer-controlled telescopes and automated observing, astronomers launched international collaborations with the goal of mapping a large fraction of the visible universe in 3 dimensions. The cosmic map that has emerged leads us out beyond our own remote corner of the Milky Way. We move through our cosmic neighborhood, a collection of 20-odd galaxies known as the local group. Beyond that, some 50 million light-years away, we approach the densely packed Virgo supercluster, the nearest intergalactic city. Beyond Virgo, galaxies line up in vast walls and arcs. Here's how this pattern plays out on extremely large scales. The universe is a spider's web of galaxy filaments bounded by immense empty voids. To explain the origin of these immense structures, scientists proposed a more expansive model of cosmic origins. It's based on the discovery that energy is constantly welling up from the vacuum of space in the form of particles of opposing charge, matter and antimatter. The new idea, called inflation, holds that the universe sprung from these diffuse energy fields. They somehow tipped into a higher energy state, causing space and time to literally inflate. Tiny fluctuations in the primordial energy generated pressure waves, or ripples. As the universe evolved, these ripples gave rise to variations in the density of matter, which gravity then began to amplify. To link these ripples to the patterns of galaxies we see around us, astronomers have been using supercomputers to simulate the evolution of the universe going back to its early days. Starting in a time when the universe was 10% its current age, the simulations show matter steadily falling into denser and denser regions, where stars, galaxies, then galaxy clusters formed. Simulations like this are designed to replicate just a portion of the visible universe. The universe as a whole is now thought to be much, much larger. The fury of cosmic inflation would have caused the universe to go from atomic size to cosmological size within an infinitesimally short time. In the billions of years since its birth, the theory says, the universe as a whole would have grown to some 10 billion trillion times the size of the observable universe. That's a 10 followed by 24 zeros. Put another way, the whole universe is to the observable universe as the observable universe is to an atom. As incomprehensibly large as the universe is in the inflationary model, perhaps that's not even the limit. Four centuries ago, Galileo showed that our sun is just one of many stars. Eight decades ago, the astronomer Edwin Hubble showed that the Milky Way is one galaxy in an ocean filled with island universes. Newer observations have revealed the immense size of our galaxy. Then, clusters of galaxies. And beyond them, vast walls and filaments of matter. By drawing on an underlying physical process to explain the birth of the universe, the idea of cosmic inflation has led scientists to think in far broader terms than ever before. There are versions of the theory, for example, that suggest we live in one of many universes that may even coexist side by side. Like bubbles, these universes are continually rising up and expanding across the oceans of infinity. This idea amounts to a quantum leap in our sense of scale. By extending our ideas of the structure of time and space far, far beyond our visible horizon. Does it push us on our tiny, out-of-the-way planet into a smaller and smaller corner of creation? Or does our ability to assemble models that describe the larger universe somehow elevate our importance in the grand scheme of things?